Hello, in this video we're going to look at a very simple, maybe an overly simple equivalent circuit of an induction motor and how we can use that to plot a torque slip curve. And it's really just to give an indication how these torque slip curves are plotted. So we begin by looking at an induction motor which is made up of a stator. So these are the stator windings here. You can see the wires. They sit inside a housing, and then in between the stator, or in the center of the stator, we will have a rotor. So we're going to use this shape to symbolize the stator, this for the housing, and this for the rotor. So when we put them all together, we're going to have something like that. Okay, so with the induction motor then, it's connected to an AC supply. And when we do that, we get a rotating magnetic field around the stator. So the supply will cause the magnetic field to rotate. And there's a separate video on that if you want to look at that. Okay, from the supply side then, the circuit might look something like this. So there's a supply voltage. The stator has some windings. They will have some inductance and they'll have some resistance R. Now, when the rotating magnetic field rotates, the flux lines are cutting these conductors, and that will induce a voltage in the rotor. And that voltage is proportional to the number of windings, first of all, and the rate at which we're cutting the flux lines. So as it moves around, it's cutting the flux lines are cutting the different inductors, okay, and inducing a voltage. However, that was slightly misleading because if I draw it, if the rotating magnetic field is rotating as the same rate as the rotor, then there is no relative motion. So I just go back there, go back a slide. We'll see this again. See, there is no relative motion. It's always in the same position. So there is no dphi dt. So what has to happen is the rotational speed of the rotor, nr, that has to be slightly less than the rotational speed of the magnetic field. So we call that difference in speed slip. So it's the difference between the rotational speed of the rotating magnetic field and the rotational speed of the rotor. Okay, so the rotating magnetic field is inducing a voltage or current in the rotor. So essentially, it's acting like a transformer. So we're getting supply voltage in, it's going through these coils. There is an air gap, and the magnetic field then is inducing a voltage on the secondary of the transformer, which is really the rotor here. Now, that voltage that is induced, that is proportional to the dphi dt, so it depended on the slip, okay, the change in speed. So let's assume here now that the voltage is SV0, and the inductive reactance of the secondary side of the transformer is 2 pi SFL. So normally inductive reactance is 2 pi FL, F being the frequency on this side, the frequency to supply voltage. But because the rotor is rotating at a slightly reduced speed due to slip, it's now 2 pi SFL. Okay, so that's my equivalent circuit here now. So the impedance here is 2 pi SFL, or we just say SX0, X0 being what it would have been if the rotor wasn't rotating at all, okay, which is just 2 pi FL. So it's S 2 pi FL is the inductive reactance. The resistance is R, so the total impedance then is R squared plus S X0 squared. And then the current in this side, I, so the I in the rotor, is the voltage, which is SV0, divided by the total impedance Z. Okay, so the power in an AC circuit is V by I cosine phi, this being the power factor. Well, V, we saw V is SV naught. I, we've just seen it's the voltage, SV naught, divided by the impedance, R squared plus SX naught squared. And cosine phi, the power factor, is R over Z, and that's R and that's Z, which we've already stipulated. So when we multiply them out, we get an expression here for the power. So I'm going to put that over to one side. If we now look at the mechanical power, so power is torque times omega. Omega is normally 2 pi the rotational speed in revs per second. But on the rotor side, that speed is going to be multiplied by the slip. Okay, so it could be 90% of that or 80% of that. So that's omega R. So the power then is the torque times, instead of omega, I'm going to put it in S2 pi N1. And we're going to rearrange that then to get the torque. And then I'm going to substitute power value in here for P. And now I have an expression for my torque. I have S here and S squared there. So I'm now left with a very simple equation for torque. And this is useful for us to understand the torque slip curve. Now we could simplify this further and just say that the torque is proportional to V squared R. So basically we're getting rid of the S and 2 pi S here. But I'm going to use this equation here. Okay, so I'm going to take that equation and I'm going to use it on a circuit where we have varying R's. So if this is our induction motor, we have an AC supply, this is our rotor, and let's say we have some slip rings and brushes where we could add in an additional resistance. So whatever the resistance of the windings are in the rotor, we could increase them by adding in this additional resistance. So I'm just going to assume that I have an X0 of 8 ohms, so an inductive reactance of 8 ohms, and we're going to look at some different resistors. So what's going to happen when it's 1 ohm, 2 ohm, 3 ohms, and so on. So we're going to look at that in Excel. So here we have it in Microsoft Excel. So I'm assuming a voltage 115 volts. N1 is 40 revs per second, and X0 is 8 ohms. So the inductive reactance is 8 ohms. I'm going to look at a very slip factors. So we're going from 10% slip up to 100% slip. And this is where the resistance is equal to 1 ohm, 2 ohm, 3 ohms, 4 ohms, and 8 ohms. So these are the various torque values. And you can see that when I plot them, so when R is equal to 1 ohm, I'm getting maximum torque at 10% slip. When R is equal to 2 ohms, maximum torque is about 23%. When it is 3 ohms, it's about 35% slip. 4 ohms, about 45% slip. 8 ohms, up around here, nearly 100% slip. So you can see the maximum torque doesn't change, right? Doesn't matter what the resistance value is, the maximum torque doesn't change. It's just where it happens in relation to slip. So why I'm interested in this is if we have an electric propelled aircraft or a drone, you can control where you want maximum torque by varying the resistance that feeds into it. So you can, that's what I'm saying, you can vary where the maximum torque occurs on the torque slip curve by varying this resistance. Okay, and then finally, that's the graph I've just shown you where we're going from 0% slip up to 100% slip, but there are occasions when they put this axis in reverse order. So you might see it this way. So the 0% slip is here and 100% slip is over there. These are different because I use different R values on when I did this. I know they show the same here, but they're actually different, and I forgot to update the slide. But that's it. That's just how it's how it's represented. I hope that's of some use.